7.1, 7.2, exponential functions and their properties. All right. This will be a very short section because we're pretty much just going to be talking about a couple things. Exponential functions are functions in the form of y equals a times b to the x power, where a cannot be 0, b cannot be 1, and b has to be greater than 0. Okay? So it has to be greater than 0 but not 1. And it must be positive. So the variable must be in the exponent. Alright, so this is an example right here of an exponential function, and you'll notice that it starts right here and it's technically going this direction. Okay, so if I had little arrows, it would be going this direction, and then this function is going left to right and it's going in that direction. You always want to read your graphs from left to right. Alright, so it's staying pretty steady across here and then it shoots up pretty fast. This would be a good example of bacterial growth because it starts out slow and then shoots up really fast, or the population of rabbits, or different things like that. This is a good example of exponential growth. Savings account, once you start saving money, and then after a while, you know, if you start saving more and more, it will go up pretty fast when the interest starts packing on. But anyway, this is an equation. Y is equal to 2 raised to the x power. In this instance, a is 1 because it's understood to be a 1 in front of that 2. B is 2. This one is, of course, an exponential growth as it is going from left to right and going up. A has to be bigger than 0 and B has to be bigger than 1. Okay, so it cannot be anything less than 1 right here. And the y-intercept will always be 0, and then the a would be whatever a is. So in this instance, this particular one would be 0, 1, okay, because this particular one has, this graph has a 1 in front of it, so that would be 0, 1. Alright, the domain is going to be all real numbers on any of these exponential functions. Domain is all real. Remember, domain is your x values. This particular one has a horizontal asymptote at y is equal to 0. So it will get closer and closer and closer to 0, but never actually 0. So that would mean the range would have to be y is greater than 0. So horizontal asymptote because it's never, never, never going to go across at 0. It's going to be really, really close, but then shoot way up. Right? Because if you had a growth, you know, you have to have something to start with. In other words, in order to have like bacterial growth, you have to have a single bacteria at least in order for it to grow. That's why it can't be 0. If you were going to do a savings account example, it would have to have at least money in order to start showing any growth. So it cannot be 0. Okay, think about it that way. Now this graph over here is an exponential decay. As you're going from left to right, it is going down, closer and closer to 0. You may even be asked questions about the end behavior as x is approaching positive infinity, y is getting closer and closer and closer to 0. Okay. Same with intervals as x is approaching positive infinity, the y is approaching positive infinity also. Alright, so this equation would be, in this particular graph, y is equal to 1/2 raised to the x power. Again, there is nothing in front, so that's an understood a is equal to 1. B is whatever is next to the x. That's 1/2, and it must be a positive fraction. Okay, it must always be a positive fraction. It cannot be 1, and it cannot be a negative fraction for it to be an exponential decay. This one is a decay. Alright, so that would be like the population, you know, some deadly disease in a population of deer, and suddenly they are dying very, very fast and almost to the point of extinction. That would be a decay, exponential decay. A has to be greater than 0, And b has to be greater than 0 but less than 1. In other words, b has to be that positive fraction. Okay, that's what that means. The y-intercept again would be at 0, whatever a is. So in this case, again, it would be at 0, 1. And the domain is going to be all real numbers again. And again, the horizontal asymptote would be y is equal to 0. The range would be all numbers greater than 0. Not greater than or equal to, but greater, because as it approaches infinity, positive infinity, it is going to get closer and closer and closer to 0, but it will never be 0. Okay? Because unless you have the whole entire population of animals completely wiped out, there's going to be something somewhere. Okay? All right, so that's exponential growth and decay. Very important that you know those graphs. And again, this is the function that you're looking at, and this will tell you what happens with the graph. All right, so an example would be 12 times 0.95 raised to the x power. 0.95 is a positive fraction. That means it's going to be a decay. Okay? The y-intercept would be at 0, 12, whatever a is. This is a. Alright? And the domain is going to be all real numbers. The range is still going to be y is greater than 0. And the asymptote will still be at y is equal to 0. Nothing changed it because there's just a stretch or a compression going on in the front. This A is what's going to do the stretches or compressions of your graph. Oops. Okay? Alright, this example over here, it's 0.25 and then times 2 raised to the x. Okay, so we have a positive b bigger than 1. This would be a growth. Okay, it's not a fraction, it's a growth. Alright, the y-intercept would again be 0 and then the a, so my a here is 0.25. Domain's all real numbers. The range would still be greater than 0 and the asymptote would still be y 0. Now, you can have translations done with these just like we've worked with on the other graphs, and the translations work very similarly. When you have the parent graph, which is y is equal to a times b raised to the x power, that can be stretched or compressed by changing a, which is what I talked about up here. So changing a makes it either compressed or stretched. So remember, compressed is going to be a fraction. So compression is a fraction. Okay, and then the stretch would be a whole number bigger than 1. You know, and now if you had a negative a, that would give you a reflection. Okay? So in the example, y is equal to 3 times 3 raised to the x power, there would be a stretch of that function by a factor of 3. This 3 right here is what is stretching it. If we had the equation y is equal to 1/3 times 3 raised to the x power, that would be a compression of a 1/3 and a reflection because it's a negative a. And then if you had y is equal to b raised to the x minus h plus k, that's where you're going to get your translations horizontally and vertically. Okay, and anything on the inside of a parentheses, that opposite of h, would translate that graph horizontally. If it was a opposite of h, say we had x plus 3, that would mean it would shift to the left 3. If it was an x minus 3, that would shift it to the right horizontally. K is going to translate or shift it vertically, and if k is positive, it's going to go up. If k is if k is negative, it's going to go down. Just like in all of our other translations that we've talked about this year. All right, so note though, when you have translations that can change the range and the asymptotes. So before you answer those questions, if it's been a translation of some sort, horizontally or vertically, then you want to check in the graph and see what the range is and what the asymptote is, okay? Whatever the range is, that's also going to be similar to your asymptote. So keep that in mind when you're looking at these, okay? Just put them in your graph and look at them, okay? Just remember, whatever that bottom y value is, that's where the asymptote horizontally is going to be. All right, so I think that explains all that we are going to do on these two sections of 7.1, 7.2. And if you have any questions, come see me in class.